So, okay, so thanks for inviting me. It's always very, very pleasant being in Marseille. And so today I would like to talk about a subject that unfortunately many of you heard already, but as I was pointing out before, I mean, I have only a finite amount of result, and it seems that lately I'm giving too many talks. So, all right. The argument is a fast slow system, and the general example of fast slow system is something like this. Let me start being very vague. So I have some slow variable and some fast variable. So imagine an ODE of this type. So when epsilon is very small, this guy moves very slowly, and the other guy instead moves at speed 1. And of course, here there is some kind of, how to say, matter of taste, because many people would rather write this in this way. Which is more or less the same. It just means that you have rescaled time. So on the left, you have a situation in which the time of the fast variable is of order 1, and here instead the movement of the slow variable is of order 1. And which one is more convenient? It depends from your taste largely. I mean, this is the same equation, it's just the time rescaling. But I'm kind of like this way of writing it because it is connected to my motivation. And my motivations, they come from statistical mechanics. And the point is that what I really, I mean, it's kind of my end game, what I would like to study, I would like to study a situation in which you have many systems that are interacting, Hamiltonian systems that are interacting weakly. And now if you have Hamiltonian systems that do not interact, then of course the single energy are conserved quantities. And if they have a small interaction, then of course the single energy are no longer conserved quantity. They will evolve, albeit very slowly. And so therefore there will be some slow motion. So Z is kind of, when epsilon is equal to 0, Z is a conserved quantity. Z dot is equal to 0, it doesn't move. And when there is some interaction, then these quantities start to move very slowly, and hopefully one can hope to be able to say something about it. So that is kind of my motivation. Another motivation that is somewhat similar, it can come from geometry. If you have, for example, a lot of geodesic flow in negative curvature, and you consider the product of them, the Cartesian product of them. All right, now, of course, this is a motion that happens on every single energy, or rather, I mean, in this case, every single velocity is conserved. But if you change a little bit the metric so that there is some, the metric is not anymore diagonal, then of course the single velocity is not conserved anymore, only the total velocity is conserved, and so there is the equivalent of some energy going from one system to the other. And now, of course, the problem here is that if you take a lot of geodesic flow in negative curvature and you consider the product, what you get is not necessarily negative curvature anymore. So now you are looking at geodesic flow not in negative curvature and not even in non-positive, and then it's not obvious what to do. So the hope is that if you look at it as a a fast-slow system, a situation in which you are kind of making a perturbation from a situation that you understand, then maybe you can say something meaningful. So that is my game, and of course it means that what are the questions that I would like to ask? The questions that I would like to ask have to do with statistical properties. So this is what we have been hearing in this conference up to now. You look at systems, then you want to know, well, what are the invariant measures? Are they ergodic? Do they mix? Usual business, okay? So this is my end game, and of course, since this is in general is a very hard problem, what I'm going to do, I'm going to concentrate on a very simple example, trying to see if I can do something in this very simple example. So, I mean, this is kind of maybe a little bit different attitude for some other talk in this conference. I'm kind of normally not very interested in kind of general theory. I'm more interested in technique and trying to develop techniques that work. And in order to try to develop techniques that work, I tend to concentrate on simple example. And of course, this has drawbacks sometimes because, for example, yeah, you can have a situation in which, for example, you developed a very nice bicycle, and then you are very happy with it, and you say, okay, now you are going to put pedal on your car, and then you find out that it doesn't work so well somewhat, right? So it looks like a very good strategy, but so there is this danger, okay? And in particular, what I'm going to talk about today is not even a bicycle, it's more like these things that kids had with three wheels in the back. I don't know how they are called in English. I mean, do you know? I mean, so this is just a bicycle for kids. That's what I'm going to talk about today. All right, so let's go back just to tell you. So here, to be more specific, the point, of course, is what kind of dynamic you have here. So this type of theory I'm going to talk about as is rules actually in classical mechanics, in how to say, celestial mechanics rather than statistical mechanics. And there the situation is in the study of quasi-integrable system, and in this situation this guy typically is a quasi-periodic motion. And then you do the theory for quasi-periodic motion. This has advantages and disadvantages, because the advantage is that the motion is very simple, and you can compute some computation, you can do it by hand. There is typically only one invariant measure, not always, but I mean, unless if there are some arithmetic conditions, then there is only one invariant measure. And so that is helpful, but on the other hand, you don't have any mixing property or anything, so this is a drawback. So, but in some sense, the theory bifurcates. So if you are looking at very regular motion, then you are more or less in situation studying celestial mechanics. And if you study a situation in which this motion is very irregular, like for example in a nose of flow or something like that, then you are in the situation that I will discuss today, which was started essentially, the study of this situation was started by Anosov essentially. So that is what I would like to consider, the situation in which this motion, for each z, if I freeze z, this is a vector field, I have some kind of simple, I have some kind of very chaotic behavior. All right? Of course, the problem is that, as I told you before, I want to consider the simplest possible example. So simplest possible example is going to be not even a ODE, it's going to be a map. It's the simplest possible example. So let me just stop, you know, the generality and get to the concrete. I will consider this. This is kind of what I would like to do, and this is what I'm going to talk about. So that you are going to be kind of disappointed, but what can I do? So this is a map from the 2 torus to the 2 torus. And the map is defined in this way. It has a parameter epsilon, is that epsilon over there. It has x. I call what there, I call the z, I call theta because it's an angle, but I mean, okay, fine. So I got used to call it theta. Now if I try to change it in z, I will make a mess. And then there is some map and then there is some slow motion. Mod 1, of course, because I am on the torus. So this is the fast motion. The one that is over there is the dynamic of x. And this is the slow motion, the dynamics of what I call z over there. And of course, I need this one to have a nicer, nice property, nice statistical property. So I ask that the derivative be always bigger than, I don't know, than 1, but let's say 2, just to be on the safe side. Okay, so this, the derivative with respect to x, of course. And let's imagine that this one actually, I want this to be smooth enough, so I need to see, let's say C5, something, some regularity. What is the optimal regularity is kind of not so interesting. All right, so that is the system I want to consider. Let me just make a few remarks. If this guy does not depend on theta, and this guy does not depend on theta, then this is a skew product. It's just negative, just enough that this does not depend on theta. So the point is that this is the fast dynamics. So if the fast dynamics is independent on the slow one, then you have a skew product, which is the case that has been studied, all right? Study up to a certain point, somewhat. I mean, it has been studied the case in which this epsilon is kind of not when epsilon goes to 0, somewhat, and epsilon is something. So it's not in the class that I'm looking at. Because if epsilon is something, then that one is a rotation on the circle with a rotation that changes depending on x. And there are several results by people on the statistical property of this system by people that are here as well. But it is not really what I want, because I want to look at a situation in which I am very close to a situation in which there is a conserved quantity. So I want to understand what happens when epsilon is small, and yeah, when epsilon is small. That's what I want to understand. Okay. So the idea is that I would like to understand this system pretty well. So I don't want just to say, well, it is ergodic, it is mixing. I would like to have some idea on what is the rate of mixing and something like that. And the question is that can one try to develop some theory that does the job? All right? So, of course, if you are, well, maybe there are mainly mathematicians, but I mean, there are also some physicists or people that used to be physicists in a previous life in the audience. And so if you are kind of, you have a physicist upbringing, then what you want to do, there is something small, you do perturbation theory, of course. But of course here there is a big problem in doing perturbation theory, because if you try to do perturbation theory, when epsilon is equal to 0, the dynamics of this variable is just identity. So identity is not something you can do perturbation theory around, because around the identity there is just everything, so it's completely nonsense, right? So the first idea is to, well, I mean, and also physicists have a very clear idea what to do in this case, right? If you want to do perturbation theory around the case that is degenerate, the thing that you do one step by hand, hoping that this will remove the degeneracy, and then you do perturbation theory. So you have to do somewhat the first step by hand. You have to understand what happens to the motion of this variable when epsilon is, at least approximately, what happened to the motion of this variable when epsilon is small. And of course, it means that you have to look at times that are of the order epsilon minus 1, because each time this moves by epsilon, so if you don't wait at least epsilon minus 1, nothing moves, so there is nothing to say. So it is very natural to introduce the variable. This corresponds to going from the left to the right, you see. I mean, I kind of like the left expression, but when I work, I really work with the right. So I mean, it's just, what can I do? I mean, all right, it's happened to me all the time. I like things that I don't do. I mean. All right, so let me just say, no, sorry, there is something fundamental that I forgot to tell you. What are the initial conditions? Yeah, sorry, this is fundamental. So, as usual, for the initial condition, so this is the dynamics. So it means that the position at time n is simply given by the iteration of the map and time. This is, everybody understands this. But what are the initial conditions? The initial condition, my understanding is the following, that there is something that moves very fast. You live in the world of theta. So theta moves at speed 1 only after you rescale the time. And when theta moves at speed 1, x moves at speed epsilon minus 1. So it moves very fast, and you have no idea to know where it is. It is just moving. So while it is reasonable to ask that theta 0 is equal to some theta star, so you just fix the initial condition for theta, it is not reasonable at all to fix the initial condition of x. So you have that x naught is distributed according to some h of x dx. Okay, some density, or maybe rho. This is some measure, where this is smooth. I don't know, C3, some 3 is a random number. I mean, you don't want to go below 1, but. All right, so this is the initial condition. So the x are distributed according to some nice probability measure, and theta is fixed. Okay, and now I want to try to understand what happened in this system, and so I want to introduce this variable I was introducing before. This one will be just theta computed in epsilon minus 1t. So I just rescaled the time. So if I look at this at time t, it means that I'm looking at my dynamics at time epsilon minus 1t. And now I have a technical problem, and my technical problem is that I would like to work with continuous function. The problem is that you can work with functions that have jump, because you can decide that you are like this. You could take this, for example, but then this thing will jump, right? It will be constant for a while, and then it will jump to the next integer, and so on and so forth, which is perfectly okay. You can look at path spaces that are discontinuous, but then in order to work, you need the Skorokhov topology. And since I never learned how to spell it, I prefer to work with the C-infinity topology, and so I want to make this continuous, all right? So I make it continuous, and so what do I do to make it continuous? I just write t epsilon minus 1 t minus epsilon minus 1 t, and then here I write t epsilon minus 1 t plus 1 minus theta epsilon minus 1 t, okay? And this, of course, this funny simple is just the floor, so is the biggest integer smaller than that, okay? So now, of course, what happens? It happens that if this guy is equal to that, this is 0, and so you have exactly that. But if this guy is close to this plus 1, then this is more or less 1, and this cancel, and then you are in the next one. So this is the polygonal interpolation of, you have a picture like this. This is time. This is theta. So you have a grid of size epsilon. Okay, and you have the value of the variable theta along this grid. And what do? I just, well, I don't know, interpolate with a polygonal. So that is my path. So this is the path of theta. And it's kind of natural to want to have a continuous path because when epsilon goes to 0, I mean, you have a lot of points between 0 and some t, and so essentially it's kind of a continuous object. I mean, not really, but I mean, you can. It's natural to do that. So the first result that you have is that now, of course, notice that this so this is a continuous function because I construct it to be continuous, and it interpolated the dynamic of the variable theta, and it is, I can also consider it as a random variable because these depend on the initial condition, and the initial conditions are random in the variable x. So this I can consider it as a random variable in this space, and that will be always my point of view. I mean, this is a random variable, the path is a path, and this is a random variable. So it means that this measure induced a probability measure on this space, and this probability measure describes the possible paths that I can get from my system. And so in particular now I can talk about weak convergence, and what happens when epsilon goes to 0, this weakly converges to some deterministic path. And the deterministic path satisfies this differential equation. This is the initial condition. Okay? And I have to tell you who is omega bar, and omega bar of theta is equal to the integral of omega x theta d mu theta x, where mu theta is the unique SRB measure of the map f theta. So these maps here, I ask that the derivative with respect to x is bigger than 2, and so it means that they are expanding map of the circle. And they are smooth, so it is well known that they have a unique measure, invariant measure that is absolutely continuous with respect to Lebesgue, is the SRB measure, is this guy. So for each theta, I have a special measure. You see, this is kind of not obvious a priori, because if you were in the case of celestial mechanics, as I said before, you would have the system of the fast variable would be uniquely ergodic. Then there is only one measure that you have to consider. Then the average, if there is an average, is necessarily with respect to this measure. There is nothing else. But once you have an hyperbolic system, you have a lot of invariant measures. So a priori it's not really clear which one you have to choose, and it turns out that the SRB measure is the good guy that you have to choose. Okay? And then you get that the behavior of this guy is very similar to the behavior of this ODE. And this is essentially a Nosov in the 60s.
Theta to have a derivative.
Sorry?
Why theta epsilon has lots of places where it doesn't have a derivative, so why do we expect theta bar to have a derivative?
Well, if you do a small computation, you will see that this is uniformly Lipschitz. Okay, so this has derivative almost surely, because it's kind of clear that it's uniformly Lipschitz, because if you take the difference between 2 points, then the difference has epsilon minus 1 term time the distance, and then it's a trivial computation that is uniformly Lipschitz.
ODE is everywhere.
That's correct. Yeah, there is, I mean, Anosov, right? Is not an idiot that did that. You need to do something. Yes, that's correct. You need to check that essentially what do you do? I mean, okay, if people want to see how to do this in the most simple possible way, there is a note that we wrote for some school. I wrote together with the Simoy. And it's just, in particular, it's done that, and I will say more. I mean, there is some Essentially, one way to do it is, these are uniformly ellipses. Since they are uniformly ellipses, they have accumulation point. And then you have to study the accumulation point if it satisfies some equation. And you discover that it satisfies this equation. And then it's smooth, because it satisfies this equation, there is only one solution over there. That's more or less the logic, but you have to work, yeah? And so you have this result by Anosov, you are all happy. But now you have to remember that my question, so this is it's called averaging, of course, right? But not surprising, there is an average. And yes, I mean, I have this, so the point is that this variable does not see this increment, but what it sees just the average of the increment, that's it. So in some sense, what I like to say is that it is true that you have to do something, but there is also a very simple hand-waving proof, which is this one. You see only the average, that's it. That is the proof, more or less, of this theorem. I gave the proof. There's not much more than that, conceptually. But now, I remind you what was my end game. My end game is that I wanted to understand the statistical properties of this system. When epsilon is small, but finite. And now I wonder, does this say something? Well, you see, this is convergence in this space. It means that I control times up to epsilon minus 1 n. But what happens? So it means that I control time here of order t. This is okay for times of order capital T. T is arbitrary but fixed. And now I look at this system and I ask myself, what are the invariant measures of this system? What are the statistical properties of this system? Well, there are two possibilities. There is the possibility in which omega is always different from 0. Then it means that I have a rotation. And then there is one invariant measure that is omega bar. 1 of omega bar, theta d theta. This turns out to be an invariant measure for that ODE. But there is no mixing, so you don't, if you start from something that is not that, it just gets transported around, so you don't really get to that. So it doesn't look very good, because from here you cannot see that there is some statistical behavior of the variable theta. There is another possibility in which there are points for which this is 0, okay? So that means that this vector field is 0 somewhere, and then of course you have invariant measures, they are the deltas at the point theta I. This is an invariant measure. It can be that this is an attracting point for the equation, can be that it is repelling. If it is repelling, then you would like to think that it should not survive, it should not matter. If it is an attractive fixed point, then you wait a time t, it means that more or less you will end up in some neighbor of this attracting fixed point. But okay, that's not very much. I mean, it's just you are, okay. You can imagine that if there is an invariant measure, it should be not too far away from the attracting fixed point, but it's just wishful thinking. There is nothing in these equations that can help you. So, if you insist in this idea that this averaging should tell you something, then the next step would be to try to do better than Anosov. Is it possible to do better than Anosov? So, let me try to, so no, this one is over there. So, of course, the idea is to look at fluctuation. So you want to see the correction. As usual, you have a limit, okay? And now that you have a limit, you want to, sorry, okay? No? That I found it. Now that you have a limit, you want to see the speed of convergence. And in order to see the speed of convergence, you have to compute correction. So what are correction? Of course, you can introduce the variable theta epsilon of t, which is simply given by theta epsilon of t, which is the true trajectory, well, the polygonalization of the true trajectory, minus the average. So this is the difference. It's just, you know that this thing goes to 0 in low, but the question is how big is it? And if you are a believer in the CLT, then you would expect this to be of the order of square root of epsilon. So you renormalize it by square root of epsilon, okay? And this is something that it is conceivable that has a limit also. And if this has a limit, then you can say something about the difference between your true trajectory and the average trajectory that Anosov tells you you are close to. So, in fact, it is possible to show that this also weakly converges to some process, but now this process is no longer the solution of an ODE, it's the solution of an SDE, rather. So, the solution... No, fuck. No? How the fuck does it work? But look, I mean, okay. I don't know why I have to use this button that this muscle are perfectly good system to move things. All right, so now the equation is the following one. So this is the SDE that you get. This sigma is a positive diffusion coefficient that is different from 0 unless omega is a coboundary with respect to f, but it's something that you can rule out easily, I mean, in some condition. So typically this one will be strictly different from 0. This is just the derivative of the averaged, which of course it exists because there is some theorem that says that not only the invariant measure mu theta exists, but is also differentiable in theta as much as you want, provided that you put an exponent over there large enough, right? I mean, and so this one is an okay function, and if you look at it, you will realize that it's very natural somewhat, this equation. Why is very natural? Because if you take the equation up there, the stochastic, the ordinary differential equation, and you imagine that you change a little bit, consider, let me write it here, consider that I change the initial condition of theta bar, okay, and I give a name to this guy, xi. Okay, then you can apply the usual theory of smooth dependence from initial condition, and you can find an equation for this one, and the equation for this one, of course, is this. This is how the variation of the trajectory due to a change of the initial condition will evolve. And this is exactly the first piece over here. So what does it mean? It means that what happens, it happens that this guy gives you kind of something like random kicks. And this is this part. It's a Brownian motion with some diffusion. So you get random kicks from the fast variable. And once you get a kick, then it gets evolved by the linearization, as you would expect. So this is very natural equation. And now you know that your variable so this, of course, is always, this weak convergence is always in C0 of the interval 0t r, okay? So still you are a fixed time, so there is a problem. But now, this is more or less equal to the average equation plus square root of epsilon theta of t. This is a random variable, this is deterministic, and that is more or less what you want. Now, this type of result here is much more recent. This is essentially what we use are a technique by Dolgopiat. You can find the detail always in these lecture notes. And this is something like I don't remember, where is it? 2005. It's some paper on averaging, which I find quite amazing, as many other papers by Dima, but it contains all kind of idea of how to study limit theorem in dynamical system, and that's, so you see, there is kind of big difference between, it's written over there, between Anosov that is in the 60s and this type of result that is in 2005. And now there are also other techniques that can be used. For example, you can try to use rough paths to get such type of result, but then you have to ask Ian. I mean, he's the expert. So, but in any case, that is the result. And here, I mean, here is just this weak convergence, but this, as such, I will not be able to use it for much. But before telling you what the result that I really need, let me just make a side remark. There is an equation that has been studied obsessively in the 70s by Friedli, Wenzel, and Kiefer, and other people, and this equation, this stochastic equation over here. Let me write in this language. Sorry. So this is again a standard Brownian motion. So if epsilon is equal to 0, then this one is just, sorry, there is no prime here. This one is just is exactly the equation that, so this is a special case of what Friedli and Wenzel have been studying. But if there is no this stuff, then this is exactly the average equation. And this one, it adds a small noise to the system. So they were studying this type of problem because they were interested in small perturbation of a deterministic system, small random perturbation of deterministic system. Okay, so if you look at this, they seem kind of similar. I mean, although I have to admit to my detriment that it took me a few years to realize that they are similar. I mean, at the beginning I didn't notice. I mean, I don't know why. I mean, it's just being stupid. But if you look at this differential equation and you wonder, well, how does it compare with this one? Then it is not so hard, if you want to be not too precise, to see that this is more or less equal to theta bar t plus epsilon, square root of epsilon, sigma t. This is exactly the same. No, not really. Okay. I put a twiddle because I don't tell you exactly what it means. But more or less, the solution of this differential equation looks very much like the solution of the equation with epsilon equal to 0, and then there is a correction that is of order square root of epsilon, and this is exactly the solution of this guy. So the solution of this equation seems to be kind of similar to the solution of, to the motion of my deterministic random deterministic system. And it is then natural to say, well, maybe I can compare the solution with of this guy with the trajectory that I am interested in. I mean, is there some relation? So this is, in fact, the result that you really would like to, and that is essentially the message that I want to convey today, is that if you want to study this type of problem, maybe it's possible to find a stochastic process that mimic your deterministic dynamics for a time that is pretty long. And then you can read some, since stochastic processes are much easier to study, then you can read some property of your deterministic dynamics out of the stochastic process. I mean, it's not guaranteed to work, but at least it's some things that you can try to do. So, but in order to do that, there is a catch, that you need to make sense of this little sign here, and you need to get some result that is not just for some fixed t, but for times that possibly are longer. So that's what we did with some people, and essentially the result, the end result is the following: that the probability that theta epsilon t minus eta of t. So here I have to put some initial condition, of course, and the initial condition is always the same. It's the same that I have here for my deterministic dynamics, right? There is no x here. I have the Brownian motion rather than x, okay? So I want to look at this one, and I want to see the probability that they are different by epsilon. Epsilon is very small. I cannot go below epsilon because if I look at my deterministic process on scale epsilon, I can see that this deterministic is not random. So the most that I can go in comparison is a scale up to epsilon. Below scale epsilon doesn't make any sense. So this is smaller or equal than epsilon to the 1/2 minus beta for each t in epsilon to the alpha, epsilon minus alpha, where beta is bigger than alpha, bigger than 0. So this is a result, is a collection of results actually, but essentially it is two papers, one by Desimoy and myself, which is in a perennial state of revision. It's like 2 years that we are revising it forever, so I don't know. I hope that I finish the revision before I die. And the other one is, this has been published, Desimoy, Poquet, me, Poquet, and work, Dennis work, okay? So these are all people that were postdoc with me and had the misadventure of being involved in this type of problem that is. Okay, so let me just tell you what about this result. This result, okay, I commented on the precision. This is the maximal precision you can opt for. Bigger precision doesn't make really much sense. And of course, this estimate is meaningful only if beta is smaller than 1/2. If beta is bigger than 1/2, this is bigger than 1, and then the proof is just 1/4 of a line. This is a probability measure, so everything must be smaller than 1, and that is the end of the proof, right? If instead you want this strictly smaller than 1/2, then the proof is like 150 pages. So there is kind of a difference between the two cases. Yeah. Then, if this is bigger than if this is smaller than 1/2, this is a positive exponent, so this probability is kind of small. And it shows that you can get alpha up more or less to 1/2. So you can control times that are of order of epsilon minus 1/2, more or less, okay? And for these times, the deterministic process is pretty close to the stochastic process, to this Wenzel-Friedlin equation. So, okay, one has done quite some bit of work to get here, and the question is, what can you squeeze out of it? Well, you can squeeze something. This I want down. Because now you can do the same type of argument that I was doing for the equation upstairs, the deterministic one. You can do it for this equation here, that I call the FW equation, and see if it tells you something. So now, again, there are two cases. The case in which omega is never 0, so the average dynamics is just a rotation. In this case, the invariant measure is the same as before. Where did I write it? I wrote it, I don't know, somewhere. Over there. Okay, it's over. If omega bar is different from 0, then the invariant measure is essentially has density 1 over omega bar. This remains true for this Friedlin-Wenzel equation, but now that is mixing. Okay, so you converge to this invariant measure. But if you compute the rate of mixing, then you discover that it's true that you converge, but you converge like e to the minus alpha epsilon t. So it takes you a time epsilon minus 1. And this is too long. I have no control, because I can control up to time epsilon 1 over epsilon minus 1/2. So this is a case I cannot handle. I mean, my result on the relation between the two processes are too weak in order to say something interesting. Well, I can still use it to compute Lyapunov exponent, which is what I will discuss in this. But I certainly cannot use it to try to do something that has to do with statistical property yet. Okay, so let's consider the other case. So, okay, fine. I'm starting kind of badly because the first exam, I mean, the first case that I consider I failed miserably. Very well. It's not a problem. Now let's consider the case in which there are theta I that are 0, and I write theta I plus or minus, because there are two possibilities. The derivative of theta I plus minus, the sign of the derivative will be plus minus. So I have, of course, I want the 0 of the vector field to be non-degenerate. It's just a genericity condition. This is kind of natural. And I want that, I distinguish between the stable and unstable fixed point. Because I expect that if I am in an unstable fixed point, here I have a little bit of noise, I will be kicked out, and then I will go away. So I don't expect that to be an invariant measure. In fact, you can see that the invariant measure of the Wenzel-Frander equation are kind of like that. So you have this theta, let me do it lower. You have, let's say, theta 1 plus theta 1 minus theta 2 plus theta 2 minus. And of course, you are on a torus, so these 2 points, this is 0, this is 1, and they are identified, okay? So if you have epsilon equal to 0, your vector field just point away from this point and point towards this guy. But if you look at the stochastic differential equation, then you discover that there is only one invariant measure, and the invariant measure will look like this. It will be more or less a Gaussian around the stable point. The spread of the Gaussian is square root of epsilon. And the relative weight of the two Gaussian depends in a complicated way from the large deviation function associated to the. Typically, it will typically happen that one is much, much bigger than the other, exponentially smaller. So one of the two typically will have a mass e to the minus epsilon minus 1, and the other one will have more or less a mass 1. So if you see it numerically, typically you just see a Gaussian somewhere around one of the fixed point with a spread of square root of epsilon. Okay? And what is the decay of correlation here? The decay of correlation here is just this. Well, this is false, what I just said. It is true if there is only one fixed point that is attractive. Then this is the decay of correlation. You converge to that point at this speed. Otherwise, at this speed, you converge to a convex combination of these two Gaussian. The problem is that in these equations, there are what are called metastable states. Metastable states are states that are stable for an extremely long time. And the reason is the following, that here you have a vector field that push inside, and here you have a vector field that push inside. So if you have an invariant, if you have a measure like this, in which you are localized nearby the attractive fixed point, what will happen? It will happen that the vector field tries to squeeze you on the fixed point, but the noise tries to kick you away. And then sometime the noise will give you a kick that is so strong that you can jump from one basin of attraction to the next. But this happens extremely rarely, and you need a large deviation for that. And so you have to compute what is the large deviation. We give you the probability of jumping from one thing to the other. And if you do the computation, you will see that the probability is of order e to the minus gamma epsilon minus 1. That's typically the probability from jumping from here to here or from here to here. And so it's clear that if the real invariant measure, for example, has all the mass here and almost no mass here, but you start with a situation like this, in which you have more or less 1/2 and 1/2, you have to wait that the mass from here jump here. And this happens with this rate. So you have to wait essentially time that is of the order e to the gamma epsilon minus 1 for the mass to adjust itself. So it means that the system has two time scales. There is one time scale in which reasonably rapidly it goes to some very low dimensional subspace. And then in this low dimensional subspace, that is here is just a subspace of dimension 2, is just the convex combination of these two Gaussian, more or less. Over there, it will go to the right weight between the two Gaussian, but very, very, very slowly. So if you are kind of not very careful, you will see, you will not see this this process. Okay, but fine. So now. But what I wanted to say is that still, this of going to a state like that happens pretty fast, essentially in a logarithmic time. If you are in a logarithmic time, then this is smaller than square root of epsilon for a time log epsilon minus 1, and then you essentially see a situation like that. Maybe the weight of the two objects are wrong, but you see something like this. And this is enough to compute Lyapunov exponent, right? Because if you want to compute the Lyapunov exponent, for example, for this system, Lyapunov exponent will have two. There are two, of course. It's a two-dimensional system. So there are two Lyapunov exponents. One, of course, is positive, because it corresponds to the fast variable, which you can see that is expanding. The other one is the central. This is a partial hyperbolic system. It has a central foliation that is more or less vertical in the theta direction. And in that direction, which is exactly this direction, if you know with respect what to do, you have just to, in order to compute the Lyapunov exponent, you have just to measure with respect to the measure, to the right measure, the SRB measure, so the central Lyapunov exponent, it will be equal to, this is just the SRB measure, for example, if you know that it exists, and then there is some formula that you can compute. And then there are some other terms. And that is more or less, this is an infinite sum, but since it is divided by power of the the derivative of the expanding map, this is a geometrically converging sum. So if you want to know if this is positive or not, it's just enough that you compute the first term, if you know what this is. You don't know what this is, but if there is an SRB measure, you know, because of this fact that you are close to the stochastic process, that it must be very close to a convex combination of Gaussian over there. So this is very close, it's essentially the same that some over, sorry. Sum over the delta at theta I minus of the same quantity. And then there is some mistake that is more or less square root of epsilon in this case. So you have just to compute this quantity here in the, and this is time, how did I call, mu theta I minus, right? This is the invariant measure of the map with this parameter, the SRB measure of the map, f, small f. Okay, so at least, I mean, normally to compute the Lyapunov exponent is not so easy, right? But here you can use this in order to compute and, okay, fine, you can compute, you are all happy. And of course, naively, I mean, again, if you are naive, so what, I'm done? Yes, I'm done, okay. Okay, so 1 minute. If you are naive like I am, you can imagine that the central exponent is always negative. Why? Well, because here you get pushed inside, right? So it's contracting, at least the dynamics the average dynamic is contracting. So you can imagine that since there is a contraction, the Lyapunov exponent is negative. These turn out to be false. There are very simple examples in which the Lyapunov exponent turn out to be positive. You compute it and it's positive. And this corresponds to the fact that the central foliation is not absolutely continuous with respect to Lebesgue, which is a phenomenon that is well known to happen when you have a partial hyperbolic system. So we have explicit example. I have no time to write them down, but they are kind of really trigonometric polynomial in which the Lyapunov exponent is positive. So let me just conclude with the final result. This is also in a different paper with the Simoy. In the case in which the central is negative, then we can describe the decay of correlation for this system, which was our end goal. Of course, you have to work again a little bit more, and the decay of correlation will be, so we can, under some condition, we can show that there is only one SRB measure with this hypothesis. And this, so this should tend to that, and we have estimate, and the estimate is e to the minus alpha epsilon over log epsilon time n if there is 1, 0. So there is only one stable fixed point. And otherwise, it is e to the minus c e to the minus beta epsilon minus 1 time epsilon, well, epsilon minus 1 time n if more zeros.
What's u in this case? What's u? The measure on the left side, where is it?
This is the measure we start with, this one. The measure I start with is the one that I described here, right? You fix theta and x is, so this is the measure mu, yeah, thanks. So this is kind of the result that you can get, which is more or less the type of result that I would like to get, and this perfectly consistent with the Freidle-Wenzel situation, because as I explained before, if there is more than one sink, then it is very difficult to go from one to another, and then you would expect that the decay of correlation is extremely slow. Instead, if there is no sink, then it should be of order epsilon, the gap, the decay of correlation. And we have a log underneath just because we are, okay. We have limited the technical capacity. So thanks a lot. Bye-bye.
Okay, so discussion is open. Any questions?
So I have two questions on the Decimoy Liverani and Decimoy Poké-Volk results. So the first is on the formulation. What you say is for fixed epsilon, we have two processes and their distribution at fixed time t satisfies this concentration. Okay. So can you say that, can you get this uniformly in t? That's a coupling between the two processes, which for which the
but
supremum
you get much worse estimate. So that is, it's something that is a very reasonable question, but we didn't investigate it because we just needed at a fixed t for the applications that we had in mind, and we were a bit exhausted getting it. So, but it's a totally reasonable question. One would like to know. Of course, you can do something very stupid. You can just use these and just use this result and put things together, right? And you get some result, but it's not very good. And I think that it should be possible. Maybe one should use maybe some Burkholder inequality. I mean, you have to be a bit more smart, and this should be possible to get some result uniform, but I don't know exactly. Yeah, certainly not with this precision. Right? You have to release. I mean, this is excessive precision. Yeah.
Thank you.
More? So if you want to apply this speed of convergence, then you need some information about eta epsilon. So eta, about the solution of this.
Yes, that we have to do, because to our amazement it was not present in the literature. I mean, we have to prove this result that shows exactly that if you look at that stochastic differential equation, then in a time that is of this order, then you are very close to a situation in which you are a convex combination of Gaussian. So you are very close to a finite dimensional subspace.
So that you do.
Yes, we prove it, yes. I thought that was something that had been proven by the, I don't know, the grandfather of Friedlin, but it's not true, right? No, I mean, I couldn't find it in the literature. Yeah. There is actually, I think, some recent result by Milton Yara in which it does something similar that it probably, from what I understand, better than what we do, but it's in a little different context and needs some translation. I didn't do it. Yeah, but you are absolutely right. The general idea is that I want to use the stochastic process in order to understand what does my deterministic process for a long time. So first step is I have to understand what does the stochastic process for a long time. Otherwise, but normally it's much easier, yes.
So, any more questions? Then thank the audience.